This workshop is really meant to be introductory. It's titled, What is Machine Learning? Demystifying Methods and Application. So the audience that I tried to prepare this workshop for includes people with little or no experience with machine learning, data science, or computer coding. So you do not need to code or know how to code in order to get something useful out of this workshop. In fact, you're only going to see, I think, one line of code, maybe this entire presentation. And that's either a good or bad thing based on why you came here. It's also for people who do have machine learning and computer science experience, but they want a broader understanding of machine learning as part of real-world data analysis in general. Also, we're going to try and answer some of the following questions to help you better understand machine learning. So what can machine learning do for your own research? What is the language you need in order to interact with machine learning or data science experts? How do you prepare data for machine learning? What is it that people like myself, machine learning experts, actually do? How do we spend our days? And what can you do yourself with little to no coding experience? Also, how do you understand, interpret, and ultimately share results that are coming out of machine learning analysis? So let's cover this workshop outline real quick. So in the morning, we're going to start really briefly with some basics of machine learning, just some essentials you really should know before we dive into the rest of the session. Then we'll focus a little bit more on the basics of biomedical data, in particular goals and challenges as they're unique to biomedical data analysis, with a particular eye to how those will impact machine learning downstream, those challenges. Then we're going to talk about the all-important preparing data. I think often we forget just how important preparing data is to the entire process. And a lot of this is going to overlap with the knowledge you would need to perform traditional statistical analysis. But I want to make sure we're all on the same page in terms of what needs to be done prior to machine learning in order to do it properly and to get the most out of it. And in that section, we're going to cover two broader categories. One is data wrangling, and one is feature processing. Then we're going to move on to everyone's favorite thing, machine learning modeling, the actual use of machine learning algorithms to generate models. We'll talk about algorithm selection and hyperparameter optimization. And if you don't know what that is, you will a little bit later. In the afternoon, after lunch, we're going to continue talking about machine learning modeling. We're going to talk specifically, spend some time on evaluation. How do we evaluate our machine learning methods? We'll talk a little bit about feature importance estimation. And then we're going to take a closer look at some specific popular machine learning algorithms to hopefully give you some fundamental intuition, if not direct understanding, of how some of these commonly used methods work. And in particular, we're going to cover decision trees and a variety of ensemble tree-based methods like random forest, and what are some of the most popular machine learning algorithms out there right now, XGBoost, CatBoost, LGBoost, if you've actually ever heard of those. And then we'll spend a little bit of time with neural networks, hopefully, again, giving you some basic intuition how they work. Then we'll cover post-analysis. What do you do after modeling? And then we'll have one final educational session on automated machine learning with the goal of how does it make things easier for all of us. And then lastly, at the very end of the day, the last hour will be a mix of Q&A, just discussion and questions, as well as a brief demo of something you can take home and play with if you want to try out machine learning yourself, and again, don't have any coding experience. And there's actually a sheet in front of you on Streamline. If at any point during the breaks or whatnot, you want to check it out, there's a couple QR codes. You can take a look at the pipeline. You can even set it up to run in a break on your laptop if you'd like. Okay, so let's dive into the basics. Let's start with essential terminology. I think it's important for us all to get on the same page because terminology can be a really confusing thing to begin with. Everyone uses different language depending on the field you're in. So first off, an instance. Here we're talking about an example or a single occurrence of something in data. So this could be an individual, a sample, a subject, or a patient. Then we have feature. This is a measurable piece of data describing some aspect of an instance. So we can also call this a variable, an independent variable, or an attribute. You'll hear me say the words that are highlighted the most during this talk. Outcome. This is an event or metric that can be observed or measured. So this is the endpoint we're usually trying to predict, or the dependent variable, also known as the class or label if we're doing classification. Then we have a model. A model, just in the most general definition, is a representation or simulation of reality. And as such, it's based on assumptions. In machine learning, we can more specifically define a model as an expression of an algorithm that represents patterns that can be used to make predictions using data. And then lastly, what's an algorithm? It's just a set of instructions or calculations or problem-solving operations for completing a task. And so this could be a computer program where you've pre-programmed a series of steps. Okay, so let's start by defining machine learning. I like this definition from Samuel Arthur in 1959. He defines machine learning as a subset of artificial intelligence in the field of computer science that often uses statistical techniques to give computers the ability to learn with data without being explicitly programmed. And here, the word learn implies progressively improving performance on a specific task. For example, making predictions on whether a patient is going to have a negative or positive outcome. The real distinction that sets machine learning apart from the broader field of artificial intelligence and computer science is that instead of programming a computer to just respond in pre-programmed ways, you have an algorithm or a piece of code that interacts with and can learn from data. And so hopefully you can see right off the bat that this is a really simple general thing. Almost like anything you can imagine that learns from data could technically be defined as machine learning. So, and the same kind of, as you'll see for artificial intelligence is true. Artificial intelligence is a wildly general term that covers a lot of things, some of which are very sophisticated and some of which are super basic. So why? Why are we interested in machine learning? In general, we want to make decisions that are automated. We want to optimize performance beyond human capabilities. We want to do this with greater speed. We want to avoid human bias, assuming that bias is absent from the data. We want our models to better adapt to new data. And in particular, machine learning is really well suited to tasks involving big data, where you have many features or instances, and data that has complex patterns under it. So there's underlying patterns between our predictive features and our outcomes of interest that may be subtle. There might be noise there. You might have interactions between variables, or you could have heterogeneous relationships. And we'll talk about complexity a little bit more in a bit. Why now? Why is this so popular right now? Why is everybody doing machine learning? Well, first off, we have a flood of available data. I think we can all appreciate just the difficulty of just collecting and managing and storing and curating data. It's a real challenge. But we also have this explosion of computing power that's been going on for many years now. In particular, now we have pretty easy and cheap access to cloud computing. There's also been a great amount of progress in the development of algorithms and the theory behind machine learning. And there's been greater interaction and support coming from industry. So it's a really good time to be getting into machine learning. What are some of the big picture goals of machine learning? In its most basic sense, machine learning is about discovering patterns or associations within data. And we want to represent those patterns using what I call useful generalizations. And we can think of these as models, as an example. Useful generalizations. You're going to hear the term generalization. It's really important, and it's a persistent idea throughout machine learning. So what is the generalization process? We start with specific examples, and then we try and simplify them to one best fit idea. So let's look at this example of some specific cartoon trees, and we want to distill them down to a generalization of what a tree is. And just as a rough example, let's imagine this is our useful generalization. This is our model of what it is to be a tree. And then once we have our model, we can apply it. we apply those generalizations to future decision making. So for example, we might be trying to conduct classification or prediction. So if we take this model of a tree and then apply it to a couple of new specific instances, right, we're trying to determine, does this fit our model of a tree or does this fit our model of a tree, and ultimately make a correct prediction. Pretty straightforward? Okay. It'll get more complicated later. So I want to take this opportunity also to address possible misconceptions you might have about machine learning. First off, I've encountered this a number of times. Machine learning is not totally equivalent to artificial intelligence, nor is it totally equivalent to deep learning. So if somebody says machine learning, they're not necessarily talking about deep learning and all of these equivalencies. The most general of these terms is artificial intelligence, and it encompasses everything inside of it. Second most general is machine learning, and the most specific of these three terms is deep learning, which is a type of machine learning, which is a type of artificial intelligence. Machine learning is not, almost never, designed to demonstrate causality. At best, the associations you find using machine learning are good candidates for causality that then you want to go test using either traditional statistics or wet lab experiments or something like that. Another possible misconception is that getting more data, more features, more instances, it doesn't necessarily ensure a better model will be trained. Right? So in particular, it might be more important to increase or attempt to increase the quality of your data and ensure that when you're doing modeling, you're making correct assumptions in order to get more out of the modeling procedure. To sort of illustrate why it's not always better to have more data, a larger number of features, if you're just adding more features, and those features aren't actually informative, like you collect you sequence all the genetic variables, but it turns out the thing you're studying has no genetic basis. You added a bunch of features, that's a bunch of noise that the machine learner has to try and chew on now. You've dramatically increased the space it has to search for a good solution. So it's only useful to add variables, if you can avoid it, if you add variables that are likely to be informative. On the other side, if you increase the number of instances, something that can happen, won't necessarily happen, is that you can increase the data heterogeneity, which means that there might be different subgroups of individuals in your data set that have different underlying patterns of association. And you can actually end up making it even harder for the modeling to be conducted well. Now, this is not always the case, but I just want to illustrate that it's not always a good idea to have more data. However, yes, in general, we do want more data. Also, machine learning can't automatically be applied to solve just any old problem. You still need to frame a problem correctly. You still need something that fits into the context of something that machine learning can do well. I made this Venn diagram a while back to try and illustrate how some of the terms you hear in these related to machine learning fit together. Over on the left, we have mathematics and statistics. And over here on the right, we have computer science, a subdomain of which is artificial intelligence, and a further subdomain is machine learning. And at the intersection of statistics and machine learning, we find data science and data mining. So this is meant to really just attempt to orient you. And I'll mention this probably a couple times during the talk, but we will make these slides available to you after the talk so that you can use them as a reference in the future. Okay, let's briefly elaborate on the difference between statistics and machine learning to the best of my ability. They are largely overlapping fields. They're both concerned with learning from data, but they do have some philosophical differences between them based on their focus and their approaches. Specifically, in statistics, which is found in mathematics, the goal is to draw valid conclusions based on analyzing existing data you have in front of you, you've sampled, that you've collected. And generally, you're trying to make inferences about a larger population from that sample that you've collected. You're also typically focusing on fewer features at once. And precision and uncertainty tend to be measures of model goodness in this area of application. On the other hand, machine learning, which is founded in computer science, is focused on making predictions or seeking patterns. Generally, they consider many features at once, and prediction accuracy is a measure of model goodness. All right, so now let's talk about different types of machine learning. We can actually categorize machine learning methods based on their learning style. This is sort of typically the first way you might categorize them. Okay. The first of which is supervised learning, where you have data that is labeled. You know the outcomes. You've collected the outcomes. Examples of this include classification, where you're trying to distinguish between two or more classes, groups, here illustrated by different shapes and colors. On the other hand, you have regression, where you're trying to predict some continuous valued outcome. And differently, in classification, the model that you're training is a boundary that separates classes, but in regression, the line is the prediction. So wherever you lie on the line, that is the prediction you get. On the other hand, we have unsupervised learning, where we have data that is not labeled, or we are ignoring the label for the purposes of this kind of analysis. This includes things like clustering and dimensionality reduction. There's also something called semi-supervised learning that's a little bit newer. I don't expect you to take away much from this, but basically you can do learning with partially labeled data as well. This is more of an emerging field, but something to consider. And then lastly, we have reinforcement learning. This is typically something that's used for multi-step problems. So gameplay, game strategy is an example. When you're playing chess, every decision you make, every move you make, you don't know right away if it's a good move or a bad move. So the feedback you get is delayed. And that's exactly what reinforcement learning is meant to handle. This is probably the most challenging area of machine learning research. Machine learning is, as I mentioned before, a general term used for a variety of algorithms. These different cartoon illustrations are meant to just kind of very generally illustrate families of machine learning algorithms, and there's quite a diversity. And they differ broadly by how they represent knowledge, the search strategy they use, the learning strategy they use, and the assumptions they make. And also, of note, each one of these, like an artificial neural network, there are many ways to implement an artificial neural network. It's a vast spectrum of possibilities in even how you conduct a machine learning analysis. And I'm not saying that to scare you away, but just to make you aware that we're still learning the best way to go about it, and people are constantly proposing new approaches. One of the biggest things that differentiate machine learning algorithms is representation. So for instance, in something like linear logistic regression, many of you are probably used to this kind of equation format where you have coefficients, for instance, the y-intercept, and then you have coefficients in front of each variable, and that's how the model is represented. You also have things like decision trees or tree structures, and we'll cover that a little bit later. Support vector machines is attempting to find a plane to separate classes as well, but it represents this in a slightly different way than something like logistic regression. We have networks for neural networks, and we even have rule-based predictors, where the model is represented as a set of very human-readable if-then rules. So there's quite a variety of ways to represent models, and this doesn't capture everything. Just to kind of switch gears for a second, I do want to take this moment to separate out the distinction between a model parameter, which we just saw in logistic linear regression, and a hyperparameter, because this is going to be useful moving forward. A model parameter is a configuration variable that's internal to the model, like we just saw in linear regression. Its value can be estimated from the data, and it's generally not specified by a practitioner. A hyperparameter, on the other hand, it's an algorithm configuration that is external to the model itself. It's sort of like a setting or a knob that you can tune to adjust how the algorithm functions. The value is not, you can't really estimate it from the data directly, and it is specified by the practitioner, whoever's running the machine learning. You can figure out good settings using some general heuristics, and this is often something that needs to be tuned during the modeling process. We need to figure out the right settings of hyperparameters to get the most out of our models. All right, and this last slide in the introduction, I just want to kind of illustrate how different algorithms try and tackle different problems. Over here on the left, we have 3 data sets that are classification problems, where we're trying to separate out blue from red circles. I don't know if you can see this terribly well in the colors, but here we have basically a linear separator there that you can roughly see. There's a line would best separate these. Here we have a circle inside a circle, and here is kind of a yin-yang pattern. And we have a set of different algorithms that were chosen, and now I'm going to show each of them attempting to discriminate between one class and the other. So first, the linear version. And you can see different examples of the algorithms deciding what area of the problem space to treat as predict one class versus the other, red or blue. And that's the shading that you see in the background. The darker the blue or red, the more certain the algorithm is that you belong to that class or the other. And you can see, just you get a rough intuition how each algorithm kind of has its own view of the world, right? The reason these all look different is they all have their own assumptions. They all have their own way to represent knowledge and learn, which ultimately gives them slightly different ways of making decisions. And you can see they all pretty much do well. There's numbers in the bottom right-hand corners that show their accuracies. They all solve the linear problem pretty easily. But then, if we have a circle inside a circle, first thing I want you to notice is linear support vector machines does terribly, right? We've immediately broken a fundamental assumption of that algorithm, which is that there's a linear relationship. And so this algorithm is never going to do well on this problem. However, it does super well on the linear problem, right? And you can see, again, how different algorithms perform here. And lastly, we have the yin-yang example. And again, you can roughly get a sense of how different machine learners try and tackle problems differently. Okay, now let's move on to biomedical data, goals and challenges. So, as I'm sure you're all aware, biomedical data can take many forms, right? We have doctor's notes, we have EHR data, we have images, video, time series data. There's a huge variety of raw data. And no, you can't just hand anything to a machine learner, unfortunately, not yet at least. Let's quickly review the most common types of data that we are dealing with in the biomedical domain. The one we are most familiar with and is the easiest to use with machine learning is tabular data, right? We have rows and columns of features and instances. You can also have networks, directed networks, or graphs that show the relationship between variables or information. You can have images, you can have video, you can have time series data, and you can have text. We're not going to go into text a lot in this workshop. That's probably going to end up being its own workshop on natural language processing. That's a whole other subfield that I am not an expert on, but we do have an expert joining our department who I think is planning to give its own workshop on that topic. But anyways, these are the most common data types we have to deal with. This is going to be really basic, but let's review the basic feature types found in tabular data. So let's separate out feature types. This actually is really important to take in consideration because when you get to analysis downstream, it really does matter how your variables are treated. And that's why I'm reviewing this. Features can be numeric, they're quantitative, or they can be categorical, qualitative. On the numeric side, variables can be continuous, if you're a programmer, like floats with decimal points and whatnot, or they can be discrete, like integers. A subclass of discrete might be binary numbers, right? And there is a quantitative relationship between the numbers. The numbering itself implies something is greater than something else. On the other side, we have categorical, which involves nominal or ordinal variables. Ordinal is you have categories, let's say like tumor stage. However, there is an implied quantitative ordering to those categories. And this is important. We also have nominal variables, where we may need to encode the variable, like race, as a number for the purposes of machine learning. However, we have no intention of a quantitative relationship between those categories. And so we need to be careful to avoid that. And then on the categorical side, the equivalent of binary would be Boolean, true or false, yes or no. Let's take a look at a specific simple data example and just identify some of the variables here. So over on the left, we have rows that are instances. These are individuals. Up on the top, we have a set of features that we're going to use to make predictions about our outcome, which in this case is diagnosis. On the far left, we might have in our data set a patient ID if it's not identified or we need that patient ID for something in the analysis. So it's important to remember that that can be in data. And if we look at some of our features, let's identify what types of variables they are. So age is a discrete quantitative variable. Zip code and sex, those are examples of nominal variables. BMI is a continuous value. Income is ordinal. And insured and diagnosis are examples of binary or Boolean, depending on how you look at them. Of course, when we're dealing with biomedical data, the big challenge is the scale of the data. We have lots of potential predictive variables coming from genomics, epigenomics, proteomics, the microbiome, EHR, mobile devices. Like, there is a ton of information we can possibly integrate together into a data set. And this leads to all sorts of challenges that I won't get into all of them today, but you can imagine there are just logistic challenges of integrating that data. Now let's cover some of the basic typical goals of machine learning within biomedical or clinical data. We might want to identify risk factors or biomarkers of health outcomes to better understand the etiology, to better make diagnoses or predict outcomes, to better target personalized medicine for preventative medicine or drug treatment selection. We also might want to develop prediction models for deployment or improve clinical efficiency, including the speed and accuracy of diagnosis and cost, right? We might simply employ machine learning models to try and reduce costs. This is the typical process that we're dealing with when we're making predictive models in biomedical research. We start with data, we apply some algorithm to it, that algorithm will generate us a model, and then we can apply that model to make predictions in the future. This is the super streamed down version of the rest of this workshop. We're obviously going to expand this a lot. What are some of the common challenges in biomedical data analysis? In particular, we're going to focus on ones that are important to think about in machine learning. Starting with cleaning and data processing. We have to worry about missing data values, combining different variable types like discrete, quantitative, all of those. What happens when we mix them together? How will that impact algorithms that we're running downstream? We need to worry about feature engineering. This is, and I'll get into detail on this later, but basically it's all about making sure that we're giving the machine learner something it can chew on, something it can work with naturally. Then analysis. We have to worry about, do we have balanced data sets? Do we have a reasonably equal number of cases and controls, for example, if we're doing classification? This can actually make it a lot easier to do machine learning if we have more of a balanced data set. However, there are ways to get around that, as we'll talk about. Covariate adjustment. This is not something that has been traditionally thought of in machine learning, but if we put all of our variables into machine learning, including our covariates, we get this wonderful predictive model. How do we understand the impact of covariates? How do we account for them to better hone in on potentially causal variance versus just associations? Computing itself, right? The raw logistics behind doing machine learning. What is the scale of the data? If somebody hands me an 8 gigabyte file, can I practically run certain kinds of machine learning? Is it going to take weeks, months, years just to finish running? Signal detection. We have to worry about noise in the data. How much actual signals in the data? Have we collected all the important variables? Are we missing predictive variables? Another thing is rare variation. Some of our features, especially in genomics, might have very rare states. Do we bother including them? How do we go about including them so that we have enough power to actually detect something interesting? And then something that we specialize in a lot, how do you detect relationships in data when they're complex? And we'll go into more detail here. Lastly, reliability. Can you interpret or explain your models? Do we understand how or why they're making predictions? Are they reproducible? Can we get these same models again? If we run this on a different data set from a different hospital, do we get the same results or similar results? And we need to make sure we're cautious to identify and account for sources of bias. Let's dive into complex patterns of association a little bit more. And we're going to do this from a genetics perspective. Over here on the left, we have a box that basically represents all possible variables. But here they're just labeled with genetic, environmental, or epigenetic variables. And over on the right, we have phenotype or outcome. And this is trying to illustrate some of the common complexities in how we relate potentially predictive variables to outcome. And so let me walk through these. First off, Mendelian. We can also refer to this simply as univariate associations, or an association between a single gene and a phenotype. Then we have pleiotropy, right here, where you have the effect of a single gene on two or more seemingly unrelated phenotypes or traits. Then we have something that we focused on a lot over the years, and that is epistasis, where you have a gene that controls or masks the phenotypic expression of some other gene. And to see this relationship between the predictive variables and outcome, you need to consider all of those features together at once. And this can be computationally challenging depending on the size of your data set. Then we have heterogeneous associations. This can include something like phenocopy, where a variation in phenotype is caused by environmental conditions that is also similar to a phenotype determined from some genetic factors. Or another way we can approach heterogeneity is genetic heterogeneity, where we produce the same or similar phenotype through different genetic mechanisms. Yeah. Let's dive a little bit more into epistasis, interactions. First off, there is a distinction between biological epistasis and statistical epistasis. Biological epistasis really refers to there's physical interactions between biomolecules, right? But statistical epistasis is referring to the epistatic interaction, the interaction effect we observe from data. And notably, observing a statistical interaction doesn't actually necessarily mean there's a physical interaction. You can have one without the other. Now let's dive into different kinds of multivariate effects to help you better understand why epistasis is so particularly challenging. So by multivariate effects, these examples are just going to look at two features at a time. So in this case, we have feature 1 represents the two colored lines, and feature 2 in blue represents either this state 0 or this state 1. So there's a couple ways we're going to group these data points to understand multivariate effects. The first and simplest is additive. So here, if we look just at the effect of feature 1 in green, so that's just looking at the difference between the black line and the red line, we see that just feature 1 has an impact on phenotype, which is the y-axis. If we look just at feature 2, right, we also see it has its own independent impact on outcome. And together we can see they both additively combine to give you an increased effect on phenotype. So they both have their own independent effect. And this is the easiest for statistical methods and machine learning methods to detect. We can also have a multiplicative interaction, right? And this is similar to additive, except the combination of the two variables gives us an exaggerated effect that we take into consideration. So again, if we look at one feature at a time, green first, we see that feature 1 has an impact on phenotype, as does feature 2. However, we can also have this scenario that I'll refer to here as crossover or masked interactions. So in this case, if we look just at feature 1, so that's the black line versus the red line, they pretty much have the same exact phenotype on average. So it looks like feature 1 has no effect on outcome. However, if we look just at feature 2, similarly, if we looked at feature 2, there is an extremely minor difference. So there might be a really, really tiny, maybe negligent main effect here. However, if we are considering both features at once, obviously the combination of these two features has a big impact on phenotype. And this is why it's so difficult to detect these kinds of relationships. And there are lots of special methods out there meant to be able to detect them. We can call these two interactions, and this one I wouldn't necessarily call an interaction. Okay, lastly, on biomedical data, let's talk a little bit about heterogeneous associations, in particular genetic heterogeneity and phenocopy. So imagine we have a bunch of subjects with a disease of interest, whatever it might be, and we don't know it, but under the surface, there are different subgroups of patients that have different underlying causal factors. And so it might look something like this. This subgroup in red might have these two genetic variants that interact with one another. Over here, you might have 3 variables in the genome. Over here, you have an environmental effect that's giving you phenocopy. It could be arbitrarily complex, right? We don't know what this looks like ahead of time necessarily, because these subgroups also might not perfectly correlate with phenotypic variation, right? These people in yellow over here might not have the most extreme phenotypes of the disease. It might be more distributed for one reason or another. Also of note, both epistasis and genetic heterogeneity are likely contributors to this general problem of missing heritability, which is important for us to develop better personalized medicine. To address that is more important for personalized medicine. To give a little bit more specific real-world example, here's an example of heterogeneity, where we have heterogeneity in patients with adenocarcinoma of the lung. And so we start off with this group of patients over here. And then we can separate out this group of patients by known driver oncogene mutations, and we can use these, people are using these to select drugs for treatment. If we hone in, and so this is an example of heterogeneity, right? We know that this group right here is more responsive to a specific drug. In particular, in this example, people with an EGFR mutation can be treated by this EGFR TK1. But of those people that are treated, you can further have heterogeneity, where people that have mutations at these other locations are known to be sensitive to the treatment. They'll respond well to the treatment, but there are other people with different levels of gene expression that are less likely to respond well to treatment. So I'm just trying to illustrate how you can have genetic heterogeneity that also links to phenotypic heterogeneity, your response to treatment or the severity of disease. And even within people that are sensitive to the drug treatment, you can dive further in, and now you might have to worry about the microenvironment of the tumor and the heterogeneity at that level, and how well all of the tumor cells are responding to the treatment. And then after treatment, you might further increase the heterogeneity of the tumor environment. So heterogeneity is a problem we worry about at all sorts of levels. All right, so we've had our general introduction, and let's see, I want to see how we are on time. Oh, we're perfectly on time, this is great. Okay, so now we're going to dive into preparing data. Where to begin? Let's solve this problem by using the big data none of us have the slightest idea what to do with. Don't worry, we all feel this way at one time or another. When I'm handed a new data set, I often feel this way. And it's okay to not understand what to do. The important thing is to take the time to understand your problem, reach out for help. But I think we all struggle with what to do with big data in particular. So sadly, machine learning analysis doesn't really work like this yet. Although plenty of us researchers are trying to move in this direction. The argument can be made that some aspects of data science will always be best completed by a human being, but we're not there yet. All right, so the slide I'm about to go through is going to outline pretty much the rest of today, the rest of the workshop. So this is going to be something I'm revisiting throughout the rest of the talk. And this is the elements of a data mining, machine learning analysis pipeline. And we're going to cover pretty much all of these components. First off, in the pipeline, define your problem. Then collect data, and so you have some raw data to start with. Then we're going to move on to the larger set of elements included in data preparation, which we're going to talk about explicitly in this section. Next, we'll move on to modeling, and then post-analysis. And hopefully, at the end, we're going to get some useful knowledge that we can put into practice. Let's go back to data preparation and take a look at what's inside there. It includes things like an exploratory analysis, data wrangling, which includes things like feature extraction, formatting, cleaning, and data integration. Also in this data preparation zone is something called data splitting, which is super important to machine learning, and we're going to cover this in a little bit more depth than some of the other topics. We also have feature processing, and this is another super critical precursor to machine learning. And this includes feature engineering, feature learning, feature transformation, dimensionality reduction, and feature selection. And we're going to go into each of those, hopefully just so at least you have a basic understanding of what they are, how they work. Obviously, in this one-day workshop, we don't have time to dive into great detail in any of these, but I want you to at least walk away having a general idea of how they all fit together and where do you go to learn more about this. Make sure you understand that it's something you should be thinking about when you're approaching data analysis. Within modeling, we have these components that we'll get to later. I won't cover them now. And post-analysis, we additionally have some further components that we'll touch on. Okay, let's dive into data preparation. Actually, right before data preparation, we have defining our problem. A problem well stated is a problem half solved. Charles Kettering. So, of course, clearly define and be able to communicate either with the people you're collaborating with or certainly with the data scientists that you want to collaborate with. Be able to communicate the problem, the associated goal, and the hypothesis. Some of this is going to be really obvious, forgive me. The nature of the data and the target outcome, right? Make sure you understand what is the nature of the variables and how do you expect them to be related to outcome? Do you expect them to be related to outcome? What is the size and quality of the data? These are useful things to be able to communicate ahead of time. And a lot of these are really important. If you're not a machine learning expert or a data science expert, you want to collaborate with someone that is, these are really useful things to think about to facilitate that interaction, that exchange in an initial collaboration. Domain knowledge. Be able to communicate, are there potential sources of bias that you're aware of? What are the reasonable assumptions you can make about your problem domain? Are there known predictors or covariates in your data set? And are there already features that you obviously know should be engineered? For instance, if you have a start and stop date of a drug treatment, you're probably going to want to engineer a duration of treatment variable, right, in your data set. And this is important when preparing to conduct machine learning analysis, either on your own or when approaching a data scientist for help. Data collection. Questions to ask. What kind of problem are we trying to solve? What data sources already exist? What privacy concerns may there be? And is the data you want to access already public, or is it something you need to gather? Where am I going to store this data? Right? Where am I going to put it? This is an often overlooked thing until suddenly you have somebody sent you a folder and you're like, oh, this is like 100 gigabytes. What do I do with this? Is the data structured or unstructured? If you don't know the difference, structured data typically comes as rows and columns, and they're numerical values. It's basically ready to analyze data, structured data. Then there's semi-structured data, which you can have tags. Websites often use semi-structured data. There's information, there's like little label tags associated with it. And then unstructured data, just raw text is a great example of this. And, well, you need to generate new data, and what is your study design going to be for gathering it? Our first pitfall. Every once in a while, I'm going to talk about a pitfall. Bad data. Bad data can lead to bad everything. Almost certainly will. What do I mean by bad data? What are some problems that are common in data? Noisy data. By this I mean, have you included uninformative features, conflicting or misleading information? Dirty data. Are there missing values? Are there errors in the data from when you collected it? Sparse data. Maybe you only have a very small sample size. There's a large number of missing values. Or maybe you have categorical features with so many categories that there's very few examples of each category. Bias data. Maybe there's selection bias in how you collected the data. Maybe there are outliers in your data set that represent not real values. There are mistakes in data collection. Or survivorship bias, right? Maybe you only had access to people that had survived the treatment, and those that didn't weren't included in the study. Duplicate data. Are some of the rows duplicated by accident? Or do you have features that are perfectly correlated with one another? Right? Maybe that are in complete linkage disequilibrium, and therefore you don't need to include all of them because a big block of them has the same exact information. So the solution here is to clearly define and understand the problem, employ exploratory analysis to help identify types of bad data, and try and apply best practices when collecting and cleaning data. This is a question I think a lot of us want the answer to. You're going to be a little unsatisfied, but let me do my best. It depends. No one can really tell you for sure. It really depends on the complexity of the problem, the complexity of the patterns in the data, the complexity of the algorithm you're using, right? Like deep learning is a very complex and powerful algorithm, but notoriously requires a bunch of training data. What is the data split ratio you're using? And we'll get to data splitting later, but basically this can impact how much data you actually have to train on. Do you want to run a replication analysis? right? Do you have data left over for the very, very end to go back to and see if you get the same results? So here is a rough guide trying to answer this question based on my own personal experience. Please do not take this as law. 100 samples per class, if you're doing classification, is a bare minimum for pretty simple machine learners. That is, if somebody comes to me with less than that, I'm like, we can run this, but you have to have a really strong signal in your data set for us to detect it, and pretty much anyone is going to question the validity of this model downstream, how well it's going to replicate, unless you can show in small sample sizes it consistently replicates. But as a general cutoff, don't turn to machine learning unless you have at least this kind of sample size. Again, it's not a rule. You can always try it. It'll be fast. That's the good news. You can always run machine learning fast if you have a small data set. 1,000 samples per class is kind of the minimum for complex machine learning algorithms like deep learning. I would say at least this, but really you're going to want more. 5,000 samples per class is the comfort zone for most average problems. This is great. If you have 5,000 samples, somebody hands me that, I'm like, this is wonderful. Let's get to it. We're going to find something cool. And 10,000 samples or more, you're on really solid ground for most machine learners. You don't really need to worry about anything. Notably, more, as I said before, isn't always better. Sometimes more is just more. Data preparation. Okay, so now we're going to dive into the actual preparation steps. Here is the outline we saw before for data preparation. What is the overall purpose of data preparation? One, to get oriented with the available data, to get the data into a format that the machine learning algorithms can work with, to identify, remove errors and bias, and to provide machine learning with the smallest set of relevant or maximally informative features as possible. Because the smaller the feature set that you give to machine learning, the easier it is to find a good model. Now, if you don't know which features are most relevant, then the worst thing you can do is remove features that are important before you get to modeling. That's the most important thing. But if you can reduce the feature space as much as possible without accidentally removing informative features, that's the ideal. Data preparation, exploratory data analysis, or EDA. This is also known as descriptive analysis. And basically, we want to analyze and investigate the data via summarizing the main characteristics of the data set, generating basic visualizations. And we do this to understand and discover patterns between the outcome and our predictive variables, or among the variables, among the features. We do this to spot anomalies, outliers, and errors. We also do this to start checking the assumptions we might want to make about our analysis, or to even test some initial hypotheses. It's a playground. Try some stuff out, see what you get, understand your data. And when do you do this? Well, if somebody hands me a data set, brand new, this is a good place to start just to kind of understand it. Make sure you're on the same page, see what's in it, what's the format, what are the variable types, what are the counts. But you can do this at multiple steps throughout data preparation, especially if you're changing your data set, as you'll see in a second, as you're adding more variables that you engineer. If you're doing feature transformations or other things to the data set, you can revisit exploratory analysis to kind of check in on your data before you get to the meat of the machine learning analysis. Machine learning pitfall, class imbalance in modeling. I mentioned this a little bit earlier. The problem here is that we might train a model using a data set with a much larger proportion of one class than another. This can influence the performance of modeling itself, our interpretation of the results, and our interpretation of the results. So the solution here is to, you have a few options. The first is to just keep the class imbalance in the data set and just make sure that you're using appropriate evaluation metrics downstream, and we will cover those later. You could also utilize undersampling. So here's our original data set, and here's the majority class, and we might just randomly pick a subset of those to get a more balanced data set. The obvious problem here is that we've lost our sample size. We're shooting ourselves in the foot in many ways and making it much harder to detect a relationship. The other option is to oversample. That is, as you might expect, oversampling the minority class. So you're basically duplicating it until you have a pretty balanced data set. Don't do this. That's my recommendation. I think it's a bad idea. This is you don't know how this is going to impact your analysis. You can try it, but just be really, really skeptical of your results because you're basically manufacturing data, right, for all intents and purposes. Data wrangling, right? So we're moving on in data preparation. This whole area of data wrangling is the process of cleaning and uniting messy and complex data sets for easy access and analysis. It's also known as data munging. Munging. It's data munging. So this is something you can do whether you're doing machine learning or not, right? If you are collecting data and trying to make it available to researchers here at this institution, you might have a whole team dedicated to data munging, right? Just gathering the data, cleaning it, getting it ready to be accessed and analyzed.
Tower, 8th floor, room 8414. Code red, South Tower, 8th floor, room 8414. Code red, South Tower, 8th floor, room 8414.
Okay, so data munging, data wrangling can include any of those things, any of these things here. We're not going to get into great detail here of all the components of data wrangling, but we will focus briefly on all of these. All right, so within data wrangling, let's talk about some of these elements. First off, feature extraction. A lot of you, depending on your data sources, this might be a really important step for you. It might be something you already know how to do really well. But basically, we want to create new features to form our new data set when we can't use the raw data directly in the machine learning analysis. So for instance, if you just have data that is not in a tabular format, or you don't have rows and columns, these new features should accurately represent that raw data, whatever it may be. And we can achieve feature extraction either manually, right, which is generally a pain, or actually applying some other kind of machine learning to do the feature extraction. And deep learning is a classic example of a set of methods that allows you to extract variables, for example, from images or audio files or many other things. So you can actually use machine learning here just to create features for downstream analysis. Or sometimes you have algorithms like deep learning that can kind of do both at the same time. And you would really want to do this when you have data like images, audio, video, unstructured text, or time series data. Next up, formatting. Really basic. Organizing information according to preset specifications. All this really is when you're going to use a specific machine learning algorithm or piece of software, is your data set in the right format for it to work with? Does it have the right file type? Is the data in the right orientation? Do you need to transpose rows and columns? Does it require a...
8414, all clear.
Does...
Code red, South Tower, 8th floor, room 8414, all clear. Code red, South Tower, 8th floor, room 8414, all clear.
Does the data set require a header? Or do you want a header in the data set? Also, do your columns include specific labels for your outcome variable, the features, the instance ID? Or do you need to have those variables in a specific position in the data set? So it's just the nuances of getting the data set ready to be run by whatever the software is you're going to run. You also might need to numerically encode your data set. Some algorithms can't handle text values. You will need to put them in a numerical format. So for example, let's say we have these text variables for the feature bridge type, just as a really rough example, and we're just going to give each one a numerical encoding. Again, this is a categorical variable. In essence, there's no quantitative relationship between these per se, but we have to give them a numerical encoding in order to pass them to machine learning. Not always, but in a number of packages. Another thing to worry about is, do we have the same uniform identifier for missing data? In general, I would avoid using numbers, because you never know when a negative 999.99 could be a real value for a feature, right? So we tend to use blank values or nans or NA or something like that. Okay, next up we have data cleaning. So this is the process of removing corrupted, inaccurate, biased, or useless records from data. I'm going to show you a tree of some different types of data cleaning to consider. Basic types include removing redundant features, features that are perfectly correlated with one another. Don't remove them all, remove all but one, right? Instances, right? If you have copies of the same instance, if they're actually not supposed to be the same values, you want to remove one. You obviously do want to keep them if they're legitimate separate patients that just happen to have the same exact information. Remove missing outcome. If you're doing classification and you have a data point that's just missing their outcome value, for your needs, it's garbage. You don't need it, throw it out. You can remove it. Remove features that are irrelevant. If you know a feature shouldn't be there, right, just get rid of it. Don't make it harder for the machine learning. And then also remove features that might be involved in data leakage. So what is data leakage? This is another ML pitfall. So a problem here is that we have information that should not be available, but it's still in the data set, the training data set that's used to train the model. So for instance, maybe you accidentally have some or all of the testing data, and we'll cover the difference between testing and training in a second. But you have some of the testing data accidentally included in the training data set. Or maybe you have features in your data set that would not be available in practice. You would, in general, only have these feature values after you put the model into practice. Or maybe you accidentally have the outcome itself or a completely outcome-dependent variable in your data set that effectively is cheating. Like it shouldn't be there, it's not information you would have. So one example of this is maybe you have a feature in your data set that is the total time until a patient is, from the ER is admitted to an ICU. And you're trying to predict admittance to the ICU, right? If you have a time to admittance, we know you were admitted, right? Solution, know your data. Understand the features in the context of the outcome you're trying to predict. Watch out for and track down causes of too good to be true performance. If you get an amazing model, immediately be skeptical. Assume something went wrong. That almost never happens. And ensure such features are excluded from your training data. Okay, a little bit more on cleaning. Removing outliers is something you can decide to do. You can either have outliers that are valid, they represent real values collected, they're just extreme, and probably you want to keep those, but you might have reasons for excluding them. Or they're impossible, right? Someone has an age of 3,000, shouldn't be there. Missing values. How do we deal with missing values? If you have a missing value in the outcome, again, just remove the instance, we covered. But if you have missing values and features, you can do a couple things. The simplest and ultimately probably the safest overall is to remove either columns that include missing values or rows that include missing values. However, the obvious downside here is that we're losing some features that might be important for making predictions, and we're losing instances, reducing our sample size. Another thing you can do is impute missing value. This is basically making an educated guess about the value based on other variables around it, or the rest of the feature values for that feature itself. There's a lot of strategies to do imputation, and often it is a necessary evil. It's just something we kind of need to do in order to move on with data analysis, but never forget that any kind of imputation is at its core data manufacturing, in my opinion, right? Because you're making hopefully an educated guess, and you might be right, but you might be adding false information there. And maybe it doesn't matter so much because the data is already noisy and we have enough issues, but just keep that in mind when you're considering using imputation. Data integration, the last part of data wrangling we're going to talk about. So this is basically combining features or instances from different data sources or from different studies. Right? So we can have data coming from lots of different sources. And some of the issues we might need to overcome is how do we overcome data silos, for example? Like how do we get the data that we need from different locations? How do we actually merge disparate data formats, right? They might have different data file types and so on and so forth. To do that integration, we might need to worry about what's called data harmonization to make sure that all of our variables have the same feature names, that the values have the same ranges and the same scaling, the same units of measurement, right? This can be an enormous task. I was involved in a project that it was just about combining 30 data sets from clinical trials, and it took 2 years with a team of like 6 or 7 of us working on this project just to put the data sets together. It can be extraordinarily challenging. And then data security, right? Just in terms of integrating data, being careful not to leak the data or make it available to people who should not have access to it. All right, so we moved on from data wrangling. Now let's focus on data splitting. You might remember this was kind of in a box on its own in data preparation, and that's because you can technically do this at different parts of a machine learning analysis. And so I'm not going to tell you exactly where to do it, but I'm going to give you tips on when to do it. So data splitting is all about partitioning available data into at least 2 parts: a training data set and a testing data set. The training data set is what's used to train your predictive model. A testing data set are the instances that you hold out to evaluate the model after the fact. Importantly, to test the generalizability of your model. How does it perform on data it's never seen? This is the only metric you should focus on in between training versus testing. Always focus on testing. So when do you do this? You can do it before any step where there is the potential to learn from instances that will ultimately be in the test set. And I have made this mistake early on in my career in terms of when do I worry about splitting my data versus when do I do these other elements of data processing. So do it certainly before modeling, but also do it before feature processing. Any kind of feature processing you do, you potentially have the opportunity for information to leak into your training data set from your testing data set. Maybe with the exclusion of feature engineering, where you're going to use your own domain experience to create new features, and you're not actually learning from the data directly. Also do this before imputation, right? Because when you impute, you're using information about the rest of the data set to make that educated guess. So if you make that educated guess before you split your data sets up, there is the possibility for data leakage, some information to leak. This is probably the best known machine learning pitfall. How many here have heard of overfitting? Raise your hands. Yeah, it's a very, very common thing to think about in machine learning. And this basically means fitting a model exactly or too closely to your training data set. You're basically going from making useful generalizations, which is the goal of machine learning, to memorizing data, which you don't want to do. Because what you'll end up doing is memorizing noise. So let's take a look at classification up here on the top and regression down here at the bottom. Again, there are 2 fundamentally different goals here. Classification, you're trying to find a boundary between the 2 classes. And here you're trying to fit the line to the data so that you're making accurate predictions on the line. And this is ideal modeling for both. In classification and regression, you want low training error, low testing error. This is overfitting, right? So we're literally memorizing the difference between one class and the other, which, depending on the data set, can be more or less useful. But it quickly can be problematic, especially if there's any noise in your data set. In biomedical data, there's almost always noise. And then you have underfitting, right? Just the opposite. This is my favorite illustration of overfitting.